Okay. Good morning. Am I audible?
Good morning, sir. Yes, sir.
Okay. Good. Okay. Let me continue the same what we discussing yesterday. This one. Yeah. I hope um you should be aware what we are discussing. This one sigma n of g. This is a set. This is a class of functions. This is what we discuss. All this class is neural networks of single hidden layer. So they basically uh, in the nature of the single hidden layer of n dimensions to one dimension. So that means like you are supplying n inputs here, and there is a hidden neurons that is a computational units that is a choice of our own, like k number of neurons. It's not a fixed thing. And then finally you are excuse me. Yeah. Finally, um, you are having a kind of a fully connected neural network, and this one. So this is from Rn to R. So whatever function you choose, that is belongs to some. This is from sigma gnet. It is basically it is in this nature. So any element which you pick it up that looks like this way, and we have defined how these uh, computations makes things, like how the affine functions are taking care with the weights associated with these edges and with the inputs, and then all the calculations that we have seen yesterday. This one especially, the mathematical expression for this. So the G is our interest. Now this G is the one which is causing a lot of things to happen with this network architecture, and not network architecture, especially the result, and how these results are going to make sense. Okay. uh, Now I would like to inquire from your side, uh, one by one, or maybe someone can answer me. Mm, what what these networks of class, or anything you pick it up. Mm, Give me one example from each one. Whoever know it, I will write it up. What this will do in the real tasks, real life. The known examples from you. The experience you may not tried it, but at least you aware, or at least you listen from the articles or news, or WhatsApp reels or YouTube reels you might see. So uh, so what is the capacity, or what capable of tasks it will do? So let me list it out from you. What are all you know, so that I can how closely they are, and what they are doing, like what exactly they are doing, and what are the pieces of components in that each task. What is Rn, and what is R here, and what is G, possible G. It will do the task for that. So okay, yeah, it's your side now. Let me list out first one.
Sir, in image recognition, sir, like if we are making any model for image recognition, if we provide a image, then their pixel, like earlier you told us last semester, sir, the our
Okay.
input is like let's guess 256 cross 256 pixel.
Okay.
something like that, sir.
Mhm. Okay. This is okay. Kind of like image recognition. Uh, so this one, mm, oops, mm, image recognition. If you take up this one, so yeah, I will come to that. Further explanation on each one and what else, like what it will do. What else? What other things? Some other. You know it already, but you have to.
Sir, they they can capture abstractions like faces, semantics, or edges from given image
Okay.
in deep learning sense.
Okay. Yeah. Of course, it is. It is a deep learning. It is like if you keep maintain several layers of this network, not just the one. That is, I think I gave you as an exercise. Yeah, this one. Construct expression for multi-hidden layer that we can talk of as a depth in depth layers and not just the one shallow layer where it mm, records or predicts several features of image, we can say. Okay. um, Capture, I will write this language. Capture uh, features of image, like as you said, the faces, edges, the depthness, those features. Each layer may take up one feature or multiple. They capture it. Yeah. And any other than image, out of the image. You can say the like a lot of things it will do.
The speech recognition.
Okay. Yeah, this okay. Those okay. These are all special cases: image, speech, or text. All these things. A lot of these are all comes under one thing, and I just want a simpler cases. These are all okay. I'm not saying they are wrong, but these are all like give the subjective domain, but in a simpler terms or simpler examples, very for coming out of the realistic world and come down to where the hypothetical or not even hypothetically, uh, let's say even from the real world. Mm,
Sir, stock market analysis.
yeah, yeah, of course, stock market, all these things will do. And you are saying big examples. That's
Sir,
fine.
function approximation.
Yeah, right. One of the thing. So you can think in a small thing. So where you can think of the better way of variables you play. Like suppose if you take our institute, your NIT Mizoram, like then you can collect the student information of their records of all their history of their grades, attendance, whatever accumulated throughout our journey during the phase of your study there. So that is entire data. That data you can take it as a input, and now you look for a function approximation for particular thing, anything like you can think of the pattern, how how each batch is performing, or the differences in the data, how regular, how suppose if we take a particular course and see the metrics over several batches and come to a conclusion, okay, whether to continue this particular course next time or not. So these things you can think on it like so in a realistic way. So what you need is a data, and you need some kind of estimations in your mind and on that particular problem, what you wanted to be predict, what your target function. That means what you are looking from the data. Based on that, you should architect your network and ask the queries and train the function and get the prediction. Anything what you do, it is a prediction, right? So data, you have to train the data and get the prediction. So like mm, so as you said, function approximation. This is just again, it's a function approximation. That is what I'm just saying. Prediction, function approximation. That means you are looking for a function, so that if you pass an input and look for the desired output. So if your function is you are looking for a boolean function, whether to uh, continue the course or not, or whether to keep continue the same structure of the syllabus or not, or same pattern of course content or not, or whether to uh, uh, continue the exam pattern of this way or not. So you have to design your own function and train accordingly, and get the approximation function and ask the result, ask your queries for unknown and get the result. That's what function approximation is. This is what you have to say. So these are all, even internally, these are all function approximations, whether you speech recognition or voice recognition or voice modulation, whatever. These are all function approximation. We are approximating a function, and then we are once we know the function and supply the unknown input and get the output. That's what we are looking at it. So in the first case, as I explained in the last semester, you have image of numbers like digits, handwritten digits of 1, 2, 3, all 0 to 9, 10 digits, and you are keep passing this into a neural network. These numbers of several thousands of numbers you are passing into it in a proper structure, and then you are looking for whether it is yes or no. That means like um, in other way to say that yes or no, the probabilistic way, like you can give the 10 outputs for each digit, one output, and whatever you this is for the 0, this is for 1, this is for 2, let's say this is for 9, and when you pass one, then it will highlight very brightly and the rest will grayly bright. They don't bright much. Even of course they also light up little. I don't say that they don't light up. Here light up means you have to define some kind of range of values, let's say 0 to 1, and when the value is close to 1, then means that is lighten up. And when value is close to zero, that is not light enough. So that we can estimate that this is the number which you are just passed to it and asking whether it is a one or not. Like that's way you can say that the given image is what is written in that, and assuming that the image contains 0 to 9, that is it. That's what we are saying. Yes. So now the question is, what's happening in this? This we are passing is okay. This you are seeing this one okay. I think you have experienced this one, the code which I have supplied last time, and again we try it today. To recap the same code and execute it and write our own image and crop it up in our phone with the desired size. I don't remember exactly what size it. I think if I remember correctly, 16 by 16. Um, so then you pass it in and get the number, get the result. Let's see whether it is true or not. You can check it up that one and write our own handwritten image and it will work out. So now the question is, uh, the cracking down what's going here to do this process. That's what today's, or maybe I hope today I will make you realize, and maybe we'll see um, the constructive proof, or we may not see also, but I will give it enough directions to come up with a mathematical formulation, because it requires a kind of heavy theorem proofs. Like I could see at least two to three theorems need to develop, mostly from the real analysis and measure theory. So I will. I'm not interested in writing proof and asking you to look at the proof and understand the proof. But the proof says very strongly that is okay constructive thing. But beyond that, that proofs is for documentation purpose, and beyond that, there is something um, that is understanding uh, what's happening in a visual way, understanding what's happening behind the mathematical lines. That's what I will try to convince, so that the proof you may forget it, but this the intuition, powerful mathematical intuition. I just wanted to break it out so that you will understand much why this is doing all this task. Okay, I'll start that. But before I start that, I need to recap few more things. Of course, I have given a lot of earlier information, measure theory, Borel measure, sigma algebra, all those things. That those are all okay. But other than those things, I need to keep few more things uh, from our real analysis. It may be a recap for you. It's not a new things. We have already discussed in our, I think, last semester real analysis. So I think not last semester, last to last semester, if I remember correctly. Am I? Real analysis was one semester before.
Yes, sir.
Yeah, right. So I think you may forget by this time, but let me recap. A definition from real analysis. Do you remember the word um, the metric, open ball, and closed ball? All those are fine. I don't touch all those, all the definitions. Only one definition I will touch, and also I hope that I don't need to repeat the open ball and all, because those are straightforward. The one definition, that is dense. Do you remember the dense? Can
Yes,
anyone?
sir.
Yeah. Can you define?
Sir, if in any set, sir,
Okay.
if we
Mm,
take any point and try to make a ball, open ball,
okay.
then
Okay.
uh, apart that point, there should be at least one point also in that ball. If for every point is satisfied, then that set is then set.
Okay. 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 Somewhat closer. Yes, close to that answer. When I will precisely write up. Um, so dense means basically we are talking dense set, dense subset. So basically we have some kind of a metric space. Let's say x comma d is a metric space, and if I say a subset y is subset of x, and a dense property whether y is dense in x or not. How do you say this one? To say uh, y is dense in x. To say given y is subset of x, to say y is dense in x, then what should qualify this y? The y should qualify the dense by the word vocabulary. The dense means it is tightly packed with x. Tightly packed with x. That means like you, uh, uh, let's say you take any open set, no matter whatever open set you choose, u from x, no matter whatever open set you choose, and there is no restriction on it. Take any open set from X from the Borel sigma algebra, I could say, but I'm not using. Use subset of X. You always have Y intersection U is non-empty. Okay, for all U. Then we say Y is dense. So that is means like this is the key, the open set. No matter whatever, wherever you zoom in, and you always find a particle from Y. Wherever you zoom in X, the X is our whole universe. That is what our metric space. In that space, wherever you zoom in, wherever you open, close microscope, keep it under a microscope, no matter wherever in the X, you always find this Y. At least a particle. You don't get any kind of empty space. That's what that denseness especially speaks. So, okay, I did not write in the formal way, but okay, you can revise your own textbook or the material, whatever I gave you, maybe almost the same notation or same symbols I use all the time, X and Y. Uh, it would be there. So now, thinking on this one example, um, to understand much concrete way, um, and
Rationals in reals.
yeah, rationals in reals. Q is Q in R is dense. Q in R is dense. That is Q is like this is a real line, and you have tightly packed rationals. All these are rational numbers. There are no gaps at all. No matter whatever whatever small neighborhood you choose, you will be having infinitely many irrationals and as well as infinitely many rationals. Okay, you don't go away with anywhere whatever open set you choose. That's what you don't find any gaps. So even if you choose irrationals, R difference Q, these are also so tightly packed. This is also dense. These two are the dense subset of R. So Q and R difference Q, these two are tightly coupled. Like that means like you have something, and okay, and you are targeting a number, and you try to isolate that number with a open interval, some open interval a comma b, and choose a and b appropriately, such that you try to isolate that number. If you try to isolate, you can't isolate at all. This number, root 2, let's say root 2, I just wanted to see uh, the pure root 2. I don't want to see any other, and keep it a comma b, the open interval, as much close as possible to the root 2. You never isolate root 2. At least you want to surround the root 2 by only irrationals, not rationals, that you can't achieve. Always there is a rational number, always it's there, whatever close. Okay, this is so fundamental thing. The q and r, reference q, are so tightly packed in r, you don't find any holes. That is, there are no holes at all in the real number. You can't see a single gap. That is the crazy part here. There is no even a small pinch of a hole. It's not there. That is what it says, denseness. Now my question is, I have a fundamental question, maybe philosophically, I reverse way of thinking. Um, like, what if, what if Q and R difference Q are not dense? This is a what if. Okay, it's of course. Fortunately, we have it dense. What if, suppose, are not dense? Can you give some guesses? What if?
Then, sir, if it is possible, then we can separate rational number and irrational
Okay,
number
yeah.
like that. So from real, like so if we are taking any interval, then
Hmm.
we can separate like
Yeah, yeah. This is that fine.
not
That is
dense.
by definition. That dense means you can find the gaps. You can isolate the numbers. You can find the root two separately without having anything in between. That you can do it. That is what not dense. But beyond that, there is one more thing I could say here at this point. I can't imagine this world with this property. I don't think of computers nowadays. We are using it. I don't think of calculus couldn't have born it without this property. I don't think that Newton or Leibniz couldn't crack any of physics without this dense property. I am saying this. Um, if I ask you simple graph, f of x equal to x square, f of x equal to x square, only at q, on q. Okay. So could you see the gaps in the graph? If I ask f of x equal
Not
to,
possible, sir. We cannot get a.
yeah,
It is not possible to draw also, sir.
not possible to draw, we can draw. F of x equal to x square on n, we can draw. On on n, we can draw. On q, we can draw. But the only thing is, on n, you just see the discrete points only. And on q also, you can write up. But these are all like, you literally can't see the gap, but there are all, of course, there are no gaps, but there are gaps. So there is a root 2, that is a gap that you can't try at the root 2. Suppose there is a number root 2 here, the root 2 you cannot touch it, or you cannot draw that. So even it looks smooth, but it is not smooth. And the may because the world which we are doing today, the physics or whatever, the so far the evolution of the scientific things, because of this continuum. If the real number system is not continuum means not having any gaps, and they are so tightly packed without any holes. That is what we are doing, the technological advancement in this. Otherwise, the physics, if you, let's say, suppose if you wanted to plot the graph of a motion of a object, like planetary objects or a simple pendulum or any kind of SHM in the physics we see in the regular daily life. mm, uh, you can't able to go to certain points. Suppose if you wanted to draw a motion of a particular path, if there are no uh, if there are some gaps in these real numbers, and you don't know what is the motion in that gap, so you can't predict it unless the speed, velocity, or the positional arguments, all these things could fail. So that is the power of this continuum. We can't imagine the world. Even I can't imagine the computers of this advancement. For example, uh, let's say you have a calculator or a computer, whatever. Um, we do a lot of tasks in the computers, like um, dealing with irrational numbers and rational numbers and a lot of things. Let's say it's a particular physical task or whatever, astronomical task, no matter whatever, definitely the governing equations brings the solutions in the form of some kind of like involving irrational numbers. Let's say there is some irrational number involved root 2 in the physical calculations. Now my question is, do you see really the real the irrational number root 2? Can you describe what it is? It is a symbolic way to, let's say, to describe x square equal to 2, the solution of this one. It is a symbol, and it is somewhere in the real number system, the root 2. And can you tell me what that number is exactly, and what it is like, not in the rational form, in the irrational form? Or maybe the pi is one of the thing that is also irrational number. Can you tell me root 2 value in a irrational format?
Sir, like decimal value is a 1.414. Then we can say, sir, like it is a number between 1.4 to 1.5.
That's okay. That number between, that's a 1.414 something, this one. But whatever you choose, the computer is doing. It is not a irrational form. It is a rational. It's a closest rational, not a irrational.
Yes, yes, sir, yes, sir.
Is a closest rational number. Suppose you are doing some kind of, let's say, some precise task you are doing, some, let's say, some robotic task or something, like, some satellite task or some astronomy task you are doing it, some engineering task where you need a precise calculation. So every microsecond or millisecond counts, and where the irrationals involved, from the calculus of point of view, and you need a close the exactly the root to achieve that preciseness, but we don't have the root to. The computers use only the closest rational, maybe whatever may be, like the root 2 is somewhere here, and you may zoom it until like say 10 rise, um, let's say 10 rise minus 1 billion, still it is irrational, right? My meaning is root 2 minus this one, root 2 plus 10 rise minus 1 billion. So you may approximate it with something with this interval range, that is so much, maybe the your decimal accuracy is maybe at 1 billionth position. That means like you taken this precisely, keep continued for 1 billion positions, still it is irrational. Still in that interval you can find many, infinitely many rationals as well as irrationals, which is still exist at the closest to root 2. You can still refine, no matter no whatever zoom you go, still I have the gap. I mean not the gap, I mean still you have chance to improve to close to root 2. You are never come across, your computers can't able to reach the exact root 2, no matter whatever may be. Still there is a infinitely many numbers in between, in that infinitely many irrationals and rationals sitting there. So but you need a preciseness root too, but we are compromised. At least maybe I could say 1 billion or 10 billion or 100 billion decimal accuracy, we are compromising it. Maybe the accuracy is very good enough, like but theoretically, analytically, we will never come across to root 2. But suppose my question where I start with this one, if this is the not dense, then now the problem. You may not find the any number in between this one. Let's say, suppose for some uh, irrational number, let's say some irrational number, I don't know, I'm not naming it any of root 2, root pi or something. Some, let's say, let me choose some sigma. It is some irrational number, some irrational number. This irrational number, I want it for at least 10 raise minus 15 for my uh, for my calculations purposes. At least 15 decimal accuracy I need it. In this interval I want it. 10 raise minus 15 to minus 15. But I said it's not dense. You don't have any number between at least 10 raise minus 3 to 10 raise minus 3. If you don't have any number, let us assume that is not dense. Not dense means you're having gaps. Then can you achieve this one, this accuracy? Hello?
No, sir.
We can't achieve. So suppose if not dense, you are flying a rocket or you are sending something, and this accuracy is not enough, then you can't do that experiment. Literally can't do it. By system itself it fails. We can't imagine this advancement of world with this dense property, without this dense property. Even I can't think of the computers, like we always play a lot of calculations. Computers takes us to the closest number, always, no matter. It approximates. We compromise sometimes like 16-bit or 32-bit or 64-bit. At least we have some precision. That is what we have, a floating point arithmetic. So we satisfy with that. So if there is no such system for some numbers, there are no numbers with that accuracy, we can't do the tasks. That is bothering. Luckily, we don't have such scenario. We are very comfortable zone. The dense the our thanks to real number system that it has uh, having its dense property. Why I am saying this story? This is very much close to our neural networks now. Okay, so now what we are doing, I am slowly moving to the neural network from this denseness understanding and denseness um, concept. Okay, before going that, I will define another one more definition. This is also a dense thing, but a slightly modified dense one. Slightly modified. Um, okay, before writing the formal writing, I will just go with because I can't write up unless I bring some visualization. Okay. So far, what we discussed is you have a bucket of water. Let's say, um, let's say you have mm, a kind of like you have a half bucket of water. Another bucket also you have. Let us assume. So now, if I combine these two buckets, this is also a water, and this is also a water. And now, what I am doing, I'm just adding this two into a one single large bucket. Okay, so that this is a mixing of both two, and it has its own water in it. This is the liquid, whatever you know. In this liquid, it has its own um, what we say the content, own particles, own molecules, whatever you say. Once you brings that into a single bucket, the same content is sitting at one place. Now, if I ask you, let's say for time being, to differentiate this water and this water in this bucket and in this bucket, I added some indicator, the color blue. Let's assume that it is a blue color water, and let us assume that it is a pink color water. And now I mix them. Okay, here this is the property of the water. They don't stay with the blue and pink. They may become different color because of the water. It dissipates the color one with the other, and the color may change. But as for the argument's sake, it is not realistically true, and hypothetically I could say that let us assume that these particles take control only the blue all the time. Then this is all the time they stay with the pink only, even when you mix it up. Okay, let us assume if it is not water, some magic liquid, and they don't change the color even you mix it up. Let us assume that that is not our subject now. So once you mix this one, you see here the blue and pink are together. The blue and pink is together. There are only two colors. So now that is well mixed. And now the question is about, if I ask you to separate it out. Uh, Now the my question is like how strongly dense they are. The resultant, that means that take any open set. Let us assume like this one. If I choose some area like this, some open set, no matter whatever ball that is, the sorry, spherical ball, whatever small radius it is, whatever epsilon, that epsilon may be, no matter whatever 10 raise minus 100 billion, it doesn't matter that small ball, you always find one blue particle and pink particle. Am I correct? Belongs to this
Yes,
U.
sir.
Let's say this is U. Then we say that if that is, no matter whatever U you choose, and if there exists a blue particle and pink particle inside you, then we say that these two liquids are dense in the when they mixed it. But of course, um, here the scenario is not the same. But for the argument's sake, for dense sake, we can say, for mathematical sense, we can say, if we are thinking of it is a some rational numbers, and you are thinking this one as irrational numbers, when you mix them, and both q and r difference q, they mixed up and ordered, because here the water or what the liquid is unordered set. But what we are talking here, real numbers, they are ordered sets, they are forming in a particular order. um, in the liquids or these kind of particles still have gaps. Why? Because I'm not sure, I don't remember exactly. The water molecule has its own atomic structure. It has its own size, some Armstrong units. I don't remember, but assume that it has very some Armstrong units of size. And you know that the liquid, if you zoom in, you will find gaps. If you recollect our material properties courses or material studies, you always find gaps. Do you know? Because of these atoms in the atomic level, the bondages, or if you go with like this kind of zooming, and you land on a particular molecule, and you don't even see any other molecules within it, because they have their own size, the precise, and you have studied this atom size, atomic sizes of each molecule or each atom. So the you go, if you take your open ball with that atomic size, and you landing on a particular atom, but you don't find any other atom of surrounding, you don't find any blue. If you may land on the blue, and you may not find any pink. So there such things we find it, but they are not so dense in this terms. But we need to mention to compromise the precision based on the atomic structural differences. So we have to choose the epsilon must be greater than, let's say, some um, 10 Armstrong units. It is not correct actually. I'm writing it for particular liquid. It is 10 Armstrong units. Then you can find the dense. So we always choose for all epsilon greater than zero. There exist u for all epsilon greater than zero. Uh, for all open balls, u uh, mm, uh, no, no, sorry. For all epsilon greater than zero, there exists a ball of epsilon at the epsilon radius at center x, and such that um, the um, ball with around intersection with that set x is not pi. This is what dense, right? The same thing I written here. The same u intersection here, I written u because U here I did not define any size. I just mentioned U is a open set, but here the open set is nothing but open ball. That is the open ball intersection. That entire this one you always find an atom, but here epsilon greater than zero. I can't have this one. The I can't enjoy this so arbitrary close to zero. I have to take up some compromise of atomic level, some length I need to precise so that I can come out of that atom and I can look at some ball so that at least a particle of other material can occupy within this. Otherwise, I will directly land on the atom. I don't have any gap to hold any other atom. That's what I could say. This compromisation is called, that is we there here, like as I explained here earlier, like if you have root 2 or sigma and you don't have any numbers in between around 10 raised minus 3, then we have to compromise with this one. There is no way you have to you are desiring this accuracy, but because of we have gaps, we have to compromise this one. The epsilon, the ball, you have to choose with this accuracy. So this accuracy, this one is talking about the accuracy, the closeness. If you have gaps, then there is no way, structurally no way, no matter whatever force you apply to go close to the sigma or go close to the item, you can't go it because it is by structure. If there are gaps, you can't find out the denseness. Okay, so nowadays the artificial intelligence is facing I told you maybe last week, is facing a lot of issues to figure out the closeness of answers because of one of these features, this closeness approximation. I will come to that why that is, but I'm just trying to illustrate before going to touch that advanced functional theories, and just the same scenarios in say the various places so that you can relate very easily in the artificial intelligence context, so that this motivation or this kind of illustrations will help you what exactly the gap means, what exactly the closeness means, what exactly the denseness means. This, you know, if you know these precise details, then you will understand that the theory, mathematical theory behind the neural networks very easily. Yeah, so now this one, why I am telling, I am not done with the definition, I have something else. Now the same scenario I will repeat with a special case. That is what neural networks use. The neural networks don't use the dense definition directly, but we use a special variation in the denseness. That's I will explain a bit here. Suppose the same illustration I will explain in a bit modification. You have water, you have another beaker of water, and doing the same thing again. You are combining it. Oh no, I don't go with this analogy because this has little issues with this analogy. I will take a small beaker of water here, no, this one, and let's say this is in the blue color. Let's say this is in the pink color. Now what I am doing, I am pouring this water into this beaker very gently, very gently. I'm not mixing it right now. I just wanted to keep it this pink water somewhere, keep it in the down and keep it here. So here already blue water is there. Let's say there is a blue water is everywhere. Now what you are doing with the pink water, you are just keeping it some place. You are not mixing now. You are putting it in some place here. Of course, there is a blue water. There is a mixer. Pink is mixing with that one. You may ask me how it is possible. It will dissipate everything and it will become spread out. But Of course, it happens after a certain time. Immediately, it won't happen. Let's assume that it is takes, let's say, some time units. I'm taking a time t equal to zero at instantaneously at some at the time zero as soon as you pour it, and let's assume that your pink is here. So everywhere the blue is there, and but in this place the blue and red is there. Blue and pink is there. Now my question is about the dense question. Let's say this entire set is X, and let's say the pink water is Y. The Y is subset of X. As soon as Y is subset of the entire water is X, so that pink is a part of it actually. So the Y is subset of X, of course. Now the question is Y dense in X? Dense in X. Forget about this error. And then we have some kind of astronomy or something you are maintaining, or forget about the thinking of that one. Let us assume in the normal way is y dense in X in this scenario. It is not mixed
No, sir.
everywhere. Yeah.
Yes,
Why?
sir.
No or
Because,
yes?
sir, no, sir, no.
Okay. Yeah. Tell me.
Because like as earlier definition, sir, if we take any u from
Mm.
x,
Yeah.
then u intersection y not equal to phi. But
Yeah.
at
Mm.
the instantaneous time, sir, when
Mm.
it's not mixed properly, then we can find some particle of water where
Mm.
only blue color present, not pink color.
Yeah. So you can find
That's
this
why,
one
sir.
so that there is no pink at all. So you can say that way is dense. So now exactly this is what we need to think on a new definition for denseness to a local definition, not a global. It is somewhere dense. It is somewhere dense. It is not dense here, but it is dense here. If you take this region only, but it is a dense, but whole part of this one, it is not possible. So then we need a special definition to define such localness. So that definition is you can think of like um, uh, so the same you can say like X. Let's say not X. Uh, yeah, X intersection Y. X intersection Y is subset of X. Right? This is our Y actually. X intersection Y is subset of X. Now the question is X intersection Y is dense in X?
Yes, sir.
You understand what I am writing in mathematically? Whatever I just explained, the X intersection Y means that means we are going closer to it. This is the Y particles are here, so X intersection Y is sitting there. So X intersection Y we are discussing. So if it is satisfying the dense property, suppose if you could able to, that means like if there exist if no not if epsilon greater than 0, there exists a ball with uh, with radius epsilon such that the ball intersection X intersection Y is non-empty. The same thing, right? For all epsilon, no matter whatever epsilon you choose, then we can say that X intersection Y is dense. So denseness property we are bring it down to local some place, not everywhere. Okay, this is what the definition of the local denseness property, or relative dense, I could say. Local and global relative density relative to a particular region, particular portion y, that is related to y only, wherever y is there. In our case, q is everywhere in the r, so that even if you take q intersection r, it is comes as same, and the whole set, it is in the rational and irrationals sitting everywhere across the real number system, so that we don't find any such localness. But in general, we don't think of that spreading everywhere, but many cases we need to look for the denseness somewhere denses. These somewhere denses are kind of like applying the dense property in a particular region. Okay, so this is all about, I could say, as much as the description of the gaps and the denseness relations with the particular reasonings. Now I will come to this one, our original starting, that is sigma n of g. Now I make a one strong statement, and that that gives you completely the understanding of why these neural networks are working. Already I gave enough details; those are sufficient to reason why the neural networks are function approximations, are why they are doing the job a great way. Okay, this one, I have some other class of function. This is a one, and another one. It is a Cn. No, Cn is set of all continuous functions, and another class of functions is set of all measurable functions. This one. Now let's see how these three are related. Can you just give a try, or spend a little 1 or 2 minutes of time to think on these three class of functions? These are all in a sigma nets, that is the description we gave yesterday, and these are all continuous functions, these are all measurable functions. Now think on them. What are these? Which one is these are our collection of baskets. Are there any common things among them? Just give a think on some time. Got something? Okay. Hello. Yeah. Do you come up with something? What are all these? This is the neural nets. This is the set of continuous functions. All continuous function from Rn to R, and uh, this is a set of all neural networks from Rn to R, and this is a set of all measurable functions from Rn to R. Can I write this one in between these number in these lines? Uh, some kind of closeness subset. For my G continuous, the G whatever I'm taking here, it is, let's assume the G is continuous.
Yes, sir. Yes, sir.
Yeah. So if you are not realizing, just think of the definitions. You don't need of any fancy mathematical deduction here. You just go through the definition of continuity, go through definition of measurable function. That is sufficient to say that this follows whatever inclusion property. So the measurable is a larger collection, and of course there are a lot of measures. I probability measure and all. And here in my case, the measure is the Lebesgue measure, and the whatever I have defined at very beginning. It is a Lebesgue measurable. This measurable functions means Lebesgue measurable. All continuous functions are Lebesgue measurable, and all neural networks are continuous. Now I'll write up something very strong notion. What I'm saying, that is, uh, the denseness I am bringing into in this case the dense property, whatever discussed there in this collection. Now I say that in a smaller context, okay, for time being, we keep this one aside. We keep this one aside, and of course, this will work for the whatever arguments we are doing. That will work for that one as well. But let us work with these two. Now I say that this I am climbing sigma n of g is dense in Cn. And of course, I should mention not everywhere, like on a compact set. On a compact set, let's say set is K. Compact set means what is the compact set? Can you recall from our real analysis? Did not define it because it is not much difficulty in this compact set. What is compact set?
The closed and bounded sets are compact set, and if we for the definition of compact sets, we have a outer circular covering, and all the balls or the smaller coverings can fit inside in that covering properly. Then that set is called compact set, sir.
Yeah, exactly. So yeah, that it has its limit points. That's in short term you can say. It do not leaving any of its limiting points. So that means like you always in our real line you can see the compact sets you can take up as closed intervals or compact sets no matter they are bounded. In a single word all limit points are containing within them, and another way of saying is it's a closed and bounded. It's closed and bounded. This is crucial. If it is not bounded, then there are a lot of issues. If it is not closed, then there are issues. We'll see them one by one. For time being, we are not touching that much importance on it, but there is a hidden things on it. Let us focus on the other piece, that is the denseness. So what does it mean? Like now you recall whatever so far we discussed, it is saying something very strongly here. Can you guess from the these discussions, whatever the water baker, all those things, that is saying very strongly here? We apply the same definition, the dense definition, on these neural nets on inside the continuous, inside of continuous functions.
Sir, like sigma n will contain every continuous function. Like it can approximate every continuous function.
Hmm. It means that the neural networks are so dense inside continuous functions. Like let us let us take a particular region. Let's say minus two to uh, two, and in this region, the closed region, the compact set region, I could say. Um, how many you can define infinitely many continuous functions, of course. Continuous functions of any kind, no matter whatever you draw it, whatever the set of collection, no matter, and these are all like everything, all constant function, this one, this one, this one, this one, no, every single trace is a continuous function. Okay? No matter whatever this is a constant function or waves of any kind, somewhere you start like this, but it must be a function. It should not violate the function definition. Um, so all these are continuous functions. Now, this one that is good, and this one is sigma nets. Sigma nets are of kind we have described the functional. Let me write up the description one more time here. That is f of x equal to, what do you write? The summation. Uh, I don't know what description we use. Let's say I equal to 1 to k, 1 to k, uh, uh, beta beta I g. The notations are same. I am trying to recall or remember or trying to recollect the same notations so that you don't bother much. Yeah, this one, g of a of x. The affine functions composed with a g is a continuous function, a particular fixed continuous function, and we have k components, and this is one such function, and there are all such. These are all varying with the a's and with the k's and with the betas. These are the three arguments which is varying this function. So these are also continuous functions, as we see here. These are all continuous functions because of, you know, fn functions are continuous, g is continuous, continuous of continuous. If f is continuous, g is continuous, f circle g is continuous. You know this one is continuous. Linear combination of product of any scalar with linear combination. That means sum of two continuous functions is continuous. So that this is a continuous. So this is a continuous function. So it's a connection. So and also these are all these are all one. Um, this is also one function which is sitting inside this one. And now the question is, if they are sitting, how this is a special collection from the CN, that is we are understanding, and this special collection, it is making something greatness is that they are sitting inside very tightly, just like Q and R difference Q, rationals and irrationals in R, how closely they are sitting, the same way these neural nets are sitting inside. That is what my claim. That is that they are dense. They are dense. They are densely packed. They are densely sitting inside CN. That means like these are all neural nets are continuous functions within inside. Like they are, no matter whatever function you choose, continuous function, you always find a close um, neural net. You may not reach like suppose you have something called function. You are doing it, you are trying to approximate something. Let's say you said like image recognition or a function approximation of something. That is that final answer is some function f of x, and if you know that f of x, then you are done. No matter whatever image you give it, it will recognize. But we don't know this f of x, but we can um, because of this denseness, what we can do, as I said earlier, like even we don't know some sigma, we can go close to this one. No matter whatever approximation you give, 10 raise minus 10 billion, I can still find a gap, closeness. Okay? So that we can go to the close to our solution. Our solution is the magic golden function for the problem of a solution of a problem. So neural networks are the great because of they are dense inside CN. If they are not dense, let us assume that if they are not dense, then there is no artificial intelligence. In single word, we could say, if they are not dense. Because of this denseness, suppose if they are not dense, means same thing. Again, you have gaps. of your problem. You can't reach because of this gap, and the closest neural net is somewhere sitting here, but it is somewhere it is very much accuracy. Let's say this is a 10 raise 2, then your function is here and you are here. G of x, you can approximate up to 100 only, but there is a large gap you can to reach your solution. You can't achieve if they are not dense. So the question and everything is sitting inside the denseness. So now you can ask me why this at very beginning. If we see, um, yeah, this one, the image is recognizing something like this one. Some other image you give it, and it is recognizing this one. That means what? This is a neural network. That is a function of some class, and this is a function. Of course, this is a function from um, some R, some K to R10. Um, yeah, I think it is 16 k to 56, I guess, if I remember correctly. What is this size which we choose in earlier, 32 or 16? 784, if I am remember correctly. So then if we have this function, so that this f of the image and gives that final answer either of one, this one, that function may definitely there exists some function in this dimension, but we don't know how to go to that function, but we are approximating through a neural network. G, this is our target function. This is our target function to achieve, to predict the image, but uh, I could say that there exists G, there exists G, um, what I could say, uh, in the dense property, there exists G belongs to sigma n of G, such that the norm of f minus G, f minus G less than epsilon, for all epsilon greater than 0. Understand what I am writing? The same definition of the density
Yes, sir.
I just written here. No matter this epsilon is defining the closeness, the zooming property, the microscopic view, and where you how close your target function you want, and you always find there exists a G. So now you decide what epsilon you want it, like what error tolerance you want it to go to that the close function you want to pick it up. And still there is a catch. The catch is uh, here, the compact set part. It is not always possible if it is not a compact set. So what is my compact set means? Like mm, suppose if I choose natural numbers as my domain, and I am looking on these natural numbers, the entire natural numbers. So you can't go because it's indefinitely goes on. They will never end up. One end is open all the time, and you are looking for a mapping one with something, two with something, three with something, and so on. And you don't know what is further down. So if you collect the data for this one, at least you don't have that unbounded data for if the set is unbounded, and if it is not closed, if it is not closed, then also there is a problem that uh, the solution of the data at this point which you are not able to provide, then it can't train for that particular point. So that is why this closed and bounded are so crucial to talk the density Otherwise they lose the denseness. They behave like, um, that those if we release the compact set notion, we can't estimate a kind of the points, the function approximating to that, the solution target function. We'll see much detailed way of versions when solving some problems. Yeah, this is the main reason. Like, I think, without any proof or without any mathematical theorem or statement, I as of now I could able to convince you that how these neural networks are working. Am I?
Yes, sir.
Yeah, fine. So I will do one thing. I don't go for proof writing or explaining step by step proof of this one. Maybe I will provide an article, or maybe I wrote this proof long back. Maybe I will find it out and draft it freshly for our case, and I will give it to you. Just go through it. I don't ask proofs for any sake, but it is a kind of like, knowing a detailed way of understanding a constructive way of design. Proofs anyway exist. That is why we are talking. So whenever you think of these neural networks or machine learning, whatever model, and you don't need to worry of as some black magic. You should think of some kind of like, okay, this is a function approximation, and there is a huge mathematical analysis is playing behind the lines, and due to this denseness property, this model is working. If the model is not sitting somewhere in the dense class, then you can't get the solutions and answers for the problems you are solving, looking at it. So the assurance is the approximation, class, the function should be uh, have some kind of density. Now we will see the practical issues. The theory is so close, and even when you, maybe this is too early for you, or maybe whether you are adapted to the proof writing of something. If you are so fascinated about mathematical deductions, and to see the step-by-step construction from the definition to properties to look at the denseness, then you feel like, once you write the proof on your own, you feel like the world is so magical, and you feel like something like, some magical power in your hand, so that you solve every problem in the world. But that is, theory satisfies, but is I say almost every time this one. But practical issues are the critical stubborns. That is not so easy to bring that theory into the practical level. Okay. Forget about the theorem proofs and all. I will supply anyway, for our sake of understand, for our sake of self-reading purpose only. Uh, Now I will move on um, with practical way of looking at the scenarios. These whatever so far the dense scenarios, especially, and the compact scenarios, and there are a lot of things I talk. This one G, the measurable functions and continuous functions. Exactly what this G is playing the role to keep the denseness. And can I say every G if I choose, is that dense is possible? That is also a thing. This okay. So let me write up a few practical issues. Whatever comes in my mind, I will write up. But I have a lot of stuff, but I can't bring everything in the short course time. But I will try my best to bring the best things. Okay. Um, the first thing. Okay. Okay, I will do one thing. I will keep it as an exercise for you, for many of them, and I will give the chance to try on our own, and then we will discuss in the next time. And I'll otherwise, it is kind of spoon feeding all the time. On this understanding of the denseness sitting inside the neural networks are sitting inside the complex, the continuous functions, I will bring the first thing, that is the functions what we have, the sigma nets, the sigma n of g equal to, this is a collection of f from uh, Rn to R, such that this f of x is defined as, I'll write up the definition like this sometimes, mm, or you can use conventional notation. The summation I equal to 1 to k beta I g of, now I will change a little bit. I don't keep as it is. Now I will change this first case. I am changing the sigma g in a special version. This affine functions aj. Okay, let me write up this aj of x as well. Then I will write up what is aj. Aj I am not keeping as same as earlier. Aj of x is earlier. What is the aj of x? W into x transpose plus b, right? Some b for real numbers. Now I don't keep this b. This is just wx transpose. The affine function, I am not keeping the constant term. Okay, I that means, like, if you think of the neural networks, you have something, you have the hidden layers of something, then you are always write up this one, and there is a bias neuron. Always this, there is a one bias neuron that is always takes up with the b1, b2, bn, or whatever bk, that I am eliminating that right now. There is no bias neuron. That is the one, that is also sigma nets, of course. That is one of the subclass, I could say. I'm eliminating that bias neuron, and rest everything same. The k belongs to natural numbers, and this aj is, of course, belong this one. But this w belongs to Rn, and what else is there? Beta is belongs to R. Yeah. Now my question is,
X.
yeah, of course, x is from R, and I don't need to mention that is f of x. We are supplying it. That's explicitly
Okay.
is there, that from the domain. Yeah, f of x. Okay. Now my question is this dense in C? That is the what? Okay, let me keep it this aside. If I just only one modification, I just removed that constant term in the affine functions. The question is this class is dense, in the CN. This is so interesting. Now you will understand the real question: why bias? You always use, you may hear, like, whenever some bias neurons. Whenever you listen any neural network video or something, there is always a bias neuron plays a role. Now you see that is dense in CN. This will make you a lot of exercise, a lot of thinking. Actually, what happens if you remove the bias? Okay, this is the first question. Is this class dense in CN? Okay, and just thinking, what else I could, yeah, major thing, and okay, I will go for another one more. These kind of questions, I don't have any limit actually. I keep pressed. If I start writing, it will never end, because the lot of variations we can create. So I'm just trying to keep bring as simple case as possible so that you can answer them in a good way, so that it will be helpful for you to understand when you are constructing your own neural networks uh, behind the lines. Yeah. Now I will bring a question on the G. This G. Yeah. The G. Now suppose. Yeah. Okay. Um, the same. The same question. Only thing is, if I change my G equal to x square. Let's say, okay, G equal to x square. Then the sigma ng, original sigma ng, not this one, not this one. This is a modified one. You can name it something sigma 1g, so that you can separate it out. Sigma 1. There is no meaning of one here. That is for my version only. So let me take this one sigma 2n. Okay, this 2 is for my sake only. The subscript 2. For the special case of g equal to x square, that means like what is the function? If you take any function f, if you take any function f belongs to this one, then how is this f of x looks like? Summation I equal to 1 to k. You have something g of beta I, g of f of x, that is g of aj of x, like this. Now g is nothing but you have something like x square, so that you can say aj of x whole square, because g is nothing but now x square, so that is composition. G is playing there. G is x square, so that you substitute aj of x in the g, so it is aj of x square. So the again everything same, except that g I modified with x square, so that it is aj of x. This class is this one. Now the question is sigma 2 ng is dense. Sigma 2 ng dense in Cn. I'm not mentioning the compact set here. You can think of any closed compact, so that you can write up like, always there is something I don't write up, but you can keep it something like Cn a comma b and a compact set. Especially you can think of like everywhere you can mention it, a comma b. That means like all functions, we are not globally minus infinity to infinity, we are not looking. We are looking at a particular piece of domain, that is a particular a comma b, I could say. Dense in Cn. Yeah. Okay. These are two theoretical questions, and okay, I will go third question for practical question. Like I urge you to like write up code and right, maybe coding point of view, look at the denseness, I could say. uh, Let us assume like a simple target function. Let's choose f of x equal to x square is our simple target function. You are targeting this x square, you wanted to approximate in this x square, let's say in on some region minus 2 to 2. Let us assume that minus 2 to 2 you wanted to approximate. That means like you are looking for a uh, neural network which approximates this one. This is minus 2, this is 2. Which neural network which approximate 2? Now, I don't want to ask you to approximate this one. There are several questions I can give it here. Like first one, on the same f of x equal to x square. What I could say, okay, you have a neural network of k size. I will give a question on now k. This k we are not touched at all. This k single hidden layer, of course, we are all discussing on the single hidden layer. Uh, okay, okay. I would like to know how many of you know this supna. Like if I have something like this one, you know this one, right? The definition of this one. Hello.
Yes, sir. In functional
Okay.
analysis we study.
Okay. Right. Fine. Okay. I don't go for these definitions so that I just supnom. I will directly give it there. So now, um, what is the least number of hidden neurons? That is, I mean, K hidden neurons. That is number K hidden neurons K. Uh, such that my target function uh, such that uh, the neural net G belongs to sigma n of G. Okay, I will give this G as well. Sigma n of G with nor f minus G is less than 10 raise uh, minus 2. Do you understand the question?
Yes, sir.
I will keep supna.
Yes, sir.
Okay. So now you have to work it out with Python. Take a neural network construction. I think I have given you that single hidden layer neural network class. You can play with that, or otherwise you can write up your own neural network. Now I am looking for you have to vary this case such that you meet the close approximation of the neural network which is sitting on this x square, such that the subnorm between this target function and this one is error is bounded by 10 raised minus 2. So yeah, that's the one thing. And of course, here I could mention what G you should use. Okay, for time being, you can use the sigmoid G. You can use it as a sigmoid. Sigma of x, 1 by 1 plus e4 minus x. That sigmoid, and I will discuss the sigmoid and all, why that special sigmoid, why it is doing task and all. We will discuss in next time. For timing, you can keep it as sigma of x equal to 1 by 1 plus 4 minus x. F of x equal to x square. Here, this x square is different. This x square is for, I just kept it as g equal to x square to say the denseness. This is not the target function. This is a activation function. I am choosing it as x square. Hmm? Okay, why can't you try using this activation function x square to approximate this x square? You can try that B. Use G equal to x square. Mm, even uh, for the same uh, in A as a next question, and you will see something great. And what else we can say? And there is something very interesting, fun fact, or maybe how many of you, fourth question I could say, how many of you use this? You use it in Python, I could say. Python. Now fourth one is not from the Python. I can ask you to use the Desmos. You know Desmos, right?
Yes, sir. Last semester we have used.
Yeah, okay. You now use the Desmos to approximate the x square even, and to see the, okay, let me open if I could able to bring that Desmos here. Yeah, this one Desmos. And okay, I think I have some GitHub things. I don't recognize. Yeah, so this one Desmos. I have this one here. Now, I think I will share this one with you so that you can. I think I have already shared. Maybe I don't remember.
Yes, sir.
Yeah,
Last semester.
yeah. I will again copy and I'll share it to you so that you can take a look at. Now the same Desmos you approximate with this one is sigmoid 1 by 1 plus e4 minus x. I have used here. So you can see the closeness. Now I have not the error I have not approximated here with something else. Now the same plot or similar draw design in the Desmos, um, but now this time not the sigmoid. You use the g of x as a ReLU of x. This ReLU is a rectified linear unit. We will discuss further sigmoid and ReLU in further classes, but this ReLU is maximum of 0 comma x. This one, and we will discuss why these are all working. Use in the Desmos and do the repeat the task of Desmos for f of x equal to x square, but use at least now use for uh, uh, okay for a equal to two hidden layers and three hidden layers and four hidden layers. It may be little hectic as you are increasing the four, but try to spend enough time, 2 3 4, using for ReLU as well as using for sigmoid. I think I have done it for two only in the my Desmos one, and now you do it for k equal to 2, 3 k equal to 3, k equal to 4, and record uh, record supnom of target function uh, for the best one. Of course, you are not coding here, but at least you can plot it, the supnom, or maybe the difference norm. You can say L2 norm or something, not the supnom. So you try for four, 2 3 4 neurons, hidden neurons in the Desmos. You don't write any program, just for f of x equal to x square for ReLU. Okay, and as well as and do emphasis on relu. And once you finish with the relu, and now uh, check with repeating the same task with g of x equal to 1 by 1 plus e power minus x for all the cases for k equal to 2, 3, 4. Now you see which one is performing and very good way. Okay, these are all tasks for you to understand literally the math behind the neural networks, the original behavior of the neural networks. So if you know this, the core details, so you will be comfortable whenever you study large things, large models, and you don't feel of like something. You are not magically reading. You are doing. You know what going behind the lines. Okay, that's it for today. You can ask me next 1 or 2 minutes. If you have any questions, then we will meet next week.
Okay, sir. Sir, please share the your this notes link again in chat because that previous link is not working, sir. It's
Okay,
showing the document is not for like that.
okay. I will share it. Uh,
Thank you so, sir. Thank you, sir.
yeah, welcome. Bye.